So can anybody relate to this? How I see math word problems. If you have 4 pencils and I have 7 apples, how many pancakes will fit on the roof? Purple, because aliens don't wear hats. Right? Sometimes when dealing with word problems, it makes about that much sense. I am here to help you. Okay? I can help you make sense of word problems. So that's good news. The bad news is there's lots of word problems in chemistry, and there's just no way around it. In fact, life is full of word problems. So, what do? Well, usually if you're given an equation to solve, you don't have too much trouble with that. The problem is getting to what you need to solve mathematically. How do you take the words and make them into equation? That requires some critical thinking, and it's going to take some practice, and you're going to make a lot of mistakes, but I think you can all do it. There's no simple formula that you can apply to every problem, unfortunately, which is how life is. There's no one solution to everybody's problems, but you can learn problem-solving strategies, and I'm going to try to teach you those. The word problems we're going to have in chemistry are going to fall into 2 groups. Either it's going to need some sort of an equation, or it's going to be a unit conversion problem. Okay, so those are the 2 sorts of problems we're going to be looking at. It's very important to learn how to convert units. I learned dimensional analysis method of unit conversion when I was a junior in high school in physics class. And I would say, looking back, that's probably the most important thing I learned in high school was how to do units. And so that's what I'm going to teach you. Dimensional analysis is a technique where the units guide you in solving the problem. And once you get used to it, it makes a lot of sense and it makes problems a lot easier. And we're going to start with some units that maybe seem kind of simple and familiar, and you may want to do the conversions a different way because it makes sense to you. I want you to do them the dimensional analysis way, because when we get to converting grams of water to grams of oxygen, your common sense method isn't going to work anymore, but the dimensional analysis will. So we always write every number with its associated unit. The unit is part of the number. We always include units in our calculations, and we cannot let units magically appear or disappear in our calculations. We can't just do stuff and then slap a unit on the end because that's what it's supposed to be. We have to treat them like algebra variables. X and Y, A and B, they cancel each other out, they multiply, they divide. You can't ignore them. They are your friends, they'll help you find your way to the correct solution. So, for most conversion problems, what happens is you're given a quantity in one unit and you're asked to find that same quantity in a different unit. And these will take this general form. There's some information that's given. You'll need a conversion factor, there may be more than one, and that will get you to the information that the question is asking you to find. So a given unit times a conversion factor will give you the desired unit. So where do we get conversion factors? Conversion factors come from equalities or equivalence statements. And here's some examples of equivalent statements. These are from table 2.3 in your textbook. 1 kilometer equals 0.6214 miles. 1 inch equals 2.54 centimeters. An inch and 2.54 centimeters represent the same length. They're just different names for the same thing. So some of these are found in tables. Some of them we use the prefixes, those metric prefixes, and we can create them just using the prefixes. So let's look at how to construct conversion factors. What is the relationship between feet and inches? 1 foot equals how many inches? 12 inches. Okay? Those represent the same length, right? Just different names. So what we can do is we can take this, which is an equation, right? This is equal to that. And a principle from math is if you do the same thing to both sides of an equality, it's still equal. So what I'm going to do is I'm going to divide both sides by 1 foot. As long as I do the same thing to both sides, it's still equal. What is 1 foot divided by 1 foot equal to? 1. Anything divided by itself is 1. So this is numerically equal to 1. If I multiply something by 1, the value doesn't change. If I take 5 feet and multiply by 12 inches over 1 foot, I have not changed the quantity. I am only changing the units. We'll get to how we put those together, but right now we're just looking at how do we make the conversion factor. So I could do it this way by dividing by feet. I could also do it by dividing by 12 inches instead. So the other conversion factor, the flip side, literally, is 1 foot per 12 inches. So this is the inverse, the upside down of that. And mathematically that's okay because 1 over 1 is still 1. Anybody have any questions? Let's look at another example, inches and centimeters. 1 inch equals how many centimeters? Anybody know? 2.54. That's a good one to memorize because we use it a lot. But most of those conversion factors in that table I just showed you, most of those, if you needed them on an exam, I'd give them to you. Because I don't want to waste your brain space with little things like that. We're going to go for big concepts. So, from this equality, I can make 2 conversion factors. I can put inch on one side and 2.54 centimeters on the other side of the line, or I can do the inverse, the upside down of that. One way to think of this is here I've got this relationship. The equal sign becomes the fraction line. So this is the fraction line. So tip your head to the left. This is on top, this is on the bottom. Tip your head to the right. This is on top, that's on bottom. The thing on the top is equal to the thing on the bottom. The number 1 stays with the unit inch. The number 2.54 stays with the unit centimeters. They have to stay together. We're going to get some practice doing these things in the online homework, and then next week in lab, we're going to have a worksheet on this. And that's where it'll really start to make sense. When you're solving problems, make sure that the final units are correct. You can sometimes go off and do all kinds of great and valid calculations and end up with the wrong unit. And that doesn't do you much good because you're not answering the question that was asked. So always check that your units are working out. Consider whether the magnitude of the answer makes sense. A lot of times students will get things upside down, and so they'll end up telling me that an inch is 5,280 miles or something. So just stop and think about it. Could that even be possible? No. Something went backwards. So then you go back and you look at your work and see what you got upside down. And then remember, conversion factors can be inverted because they are equal to 1. The numerator equals the denominator. So you can flip them upside down, and that is absolutely fine. Your book talks about a solution map. That's just a visual outline that shows your strategy for getting from the given unit to the final unit. Any of you guys ever watched Dora the Explorer? Yeah, annoying little girl, fascinating to young children. Right? So Dora the Explorer is always trying to get from one place to another, and they can't figure it out. And who do you call when you don't know which way to go? The map. The map comes in and he sings his little song and he says, oh, well, if you want to get to the snowy mountains, first you have to go over the babbling brook, and then you have to go through the scary woods, and then you'll get to the snowy mountains. That's the solution map. That's the path. This is our plan. We're going to go from here to there. And once you have that in place, the rest of it becomes much simpler. When we're doing unit conversions to solve a problem, the solution map focuses on what units we're converting. Another way to think of it is trying to get across a stream. You're on one bank, and maybe that's inches, and you need to get to the other bank, which maybe is kilometers. If you know a direct relationship, you can jump straight across. But if you don't know a direct relationship, you may have to take some stepping stones and just go partway across. Maybe you'll go from inches to feet, and from feet to meters, and from meters to kilometers. There are different paths that you can take to get to the same answer. Some of them are longer and some of them are shorter. But if it gets you there, it's okay. So what might this look like? So a simple example, converting from inches to centimeters. So this is what we're starting with. We draw an arrow to what we're trying to find, and then they're writing down what the conversion factor is. In order to go from inches to centimeters, we have to have the relationship between them. If you're converting from centimeters to inches, you're starting with centimeters, you're going to inches. This conversion factor is going to be upside down of the one used for this. So right now, don't get hung up on exactly what that is. We're focusing on, I'm going from here to there. So general strategy, figure out where you're starting. You can't go on a journey if you don't know where you are. We were in Minnesota this summer, went to the Mall of America. Ginormous mall, right? And they've got these maps all over the place. And you go stand there and look at the map, and it doesn't help at all until you find that little red thing that says you are here, right? You need to know where you're starting. The next thing is you need to know, where am I trying to go? Then you can figure out how to get there. So in these word problems, read through the whole thing, then figure out, what am I starting with? What am I trying to find out? And then how can I get there? So the given, the solution map, how to get there, and what we're trying to find. These slides are a bit repetitive, but they are what they are. Anyway, so first we sort. Figure out what kinds of information is given. Usually this involves numbers. So you read through the problem, and maybe you don't immediately see where you're starting from. Take all the numbers and write them down, sort them, figure out what they represent. And then strategize. So you figured them out, now we're strategizing, then we're solving. That's the actual doing the math part. And then the last step is really important. Check. Does the answer make physical sense? Are the units correct? Always check the significant figures. If you're doing, some study and you're trying to find out the average number of people in a family, and you come up with 0.73 people per family, does that make physical sense? No. That means you probably did your calculation wrong. Go back and look at it, okay? That can save you a lot of points on an exam, looking at your answer and saying, oh, wait a minute, that doesn't make any sense at all. So let's do some examples. Let's convert 56.0 centimeters to inches. So this is a very short word problem, right? There's not that many words in this one. Well, there's one number. That's probably what we're supposed to start with. So we're starting with centimeters. That's the unit, 56 centimeters. And what are we trying to find? Inches. So this is what we're starting with. This is what we're trying to find. If we know a relationship between centimeters and inches, we can do this in one step. Do we know it? Is there one? Even if you don't remember, hopefully, yeah, 1 inch equals 2.54 centimeters. You know, if you're looking and finding it, you might as well just write it down there. Okay, so I have a relationship between inches and centimeters, so I can go from centimeters directly to inches. So that's all the sorting and the strategizing. Now I'm going to write the equation. This little solution map is going to tell me what to do. So here's my unit that I'm starting with. It was 56.0. So I start with 56.0 centimeters. And then I look at how many arrows are there in my solution map. Well, there's only one. That tells me I need one conversion factor. This is a one-step problem. So there's my one conversion factor for that arrow. These are the units that go on the top. Centimeters to inches. You can imagine Dora saying, centimeters to inches, centimeters to inches, right? So here's centimeters. What goes here? Inches. So I put inches there. In dimensional analysis, we put the units in first, and once we get all the units straightened out, then we put the numbers in. The units tell us where to put the numbers. We don't have to remember, oh, should I multiply? Should I divide? The units are going to tell us. So I've got centimeters to inches. Now, what I want to have happen is I want these centimeters to disappear. I need to get rid of that unit. And the way I can do that is by dividing by centimeters. So if I put centimeter in the denominator over here, and I'm just looking at the units, that centimeter and that centimeter are going to cancel each other out. Centimeter divided by centimeter equals 1, and so we say it cancels out. So now the only unit left here is the unit I'm trying to find. So this is good. We got all the units in place. Now we put the numbers in. Where do the numbers come from? They come from our relationship here. 1 inch. I need to keep those two together. So the 1 goes on top with its unit, and the 2.54 goes in the denominator with its unit. So this part goes here, and this guy comes to the bottom. Common mistake is students will put the number 2.54 on the top and the 1 on the bottom. But that just doesn't work. We need the top to be equal to the bottom. So now we get out our calculators. Which I forgot to get mine out. Always a good idea to bring your calculator with you to class. So we've got 56.0. And the way you solve these is you just go from left to right. When you come to a fraction, multiply by the top, divide by the bottom. So some people recognize, well, I don't really need to put in times 1 in my calculator because it's not going to change anything. You're right, you don't need to. But if you're a very literal, concrete person and you say, but there's a 1, I need to multiply by the 1, go right ahead. It's not going to hurt anything. Okay? So 56 times 1, if you like, divided by 2.54 equals, and then my calculator is giving me 22.04724409. And the unit is inches. Could that number 22, is that physically reasonable? 56 centimeters, 22 inches, yeah, there's nothing to suggest that that's not reasonable. If we came up with 22 million, that'd probably be off, or 0.0022. What else do I need to do? Significant figures. This is an example of an exact relationship between the English system and the metric system. There's very few of them. And so I'm not going to try to trick you with this, but I do want to point that out so that if you think I'm doing something wrong later, well, it's because this is exact. Because this is exact, when we look at this conversion factor, we just ignore it for significant figures. So then all we have to do is look at the initial number and say, well, how many significant figures does that one have? 3. Okay, there's one of those pesky trailing zeros. Trailing zeros, if there's a decimal point, you count it. If there's no decimal point, no count. Okay, so there's a decimal point we're going to count. So that's 3 significant figures. Then I need to keep 3 significant figures in this one. So there's this third one, and so I'm going to rewrite this answer as 22.0 inches. Any questions? Yes?
If it was a 5, would you round up?
Yes. If it was 22.057, then you'd round up to 22.1. And you're going to get some practice in rounding and significant figures in lab this week. The Monday people, it was coming out their ears yesterday, but I think some of them learned a few things. Any other questions?
So let's say the 0 was like a 1.
Mm-hmm.
And then the force of the same would go down to 0.
So I think what you're asking is, what if the number we're rounding is 22.147? Is that what you're asking? So we'd be keeping this digit. We look at the one that we're getting rid of, and so we just chop it off. And so then we'd have 22.1. Okay? Any other questions? Let's do another example. This one's using the metric system. Convert 5,678 meters to kilometers. This reminds me of a joke. Except that I'm only remembering the punchline. Why was 6 afraid of 7? Because 7 ain't 9. Sorry, that was a complete waste of class time. Okay, so again, another short word problem. I read it. Where are we starting from? Meters. Meters is lowercase m, miles is mi. And then we're trying to find kilometers. Right? Those are the only 2 units given. If you're having a hard time finding out where to start, the unit that has the number is where you're going to start. And the unit that doesn't have the number is what you're trying to get to. So now we have to ask ourselves, well, can we get from meters to kilometers in one step? And the answer is yes. This is a metric conversion. So what I tell students is look at these 2 units and see how many prefixes are there between the 2 of them. Does this one have a prefix? No. Does this one have a prefix? Yes, it's got kilo. 1 prefix, 1 step. We'll see some others where there's 2 prefixes. Like if you were going centimeters to kilometers, then you have 2 prefixes, you do it in 2 steps. But this will be just 1 step. So we start with the starting point, 5, 6, 7, 8 meters. How many arrows in my path? 1. So I have 1 conversion factor. Dora's little chant here is meters to kilometers. So down here, I write meters to kilometers. That's not so bad. What goes on the bottom? Meters. This unit needs to be on the bottom because I want it to go away. So I'm going to put meters down there. And then I encourage you to actually draw the lines and cross the units out. So now my units are right. I'm going to end up with kilometers, which is what I was trying to do. Now we have to do the relationship between kilometers and meters. What does kilo stand for? 1,000 or 10 to the 3. I'm going to use one way of doing metric prefixes. It's not the only way, but it's a way that if you follow it consistently, it always works. And I think that's an advantage. So if you want to do it a slightly different way and you get the right answer, that's fine. But I'm not going to try to confuse people. So kilo means 10 to the third. I need what's in the numerator to equal what's in the denominator. A meter is not the same length as a kilometer. Kilometer's more like a mile size, and meter's more like a yard size. So instead of trying to think about, well, which one's bigger and which one's smaller, we're just going to follow a pattern. Kilo is on the top, kilo times meter. On the bottom, I'm going to substitute the number that kilo stands in for. So I'm going to put 10 to the 3 in the denominator, because kilo is short for 10 to the third. And so 1 kilometer is equal to 10 to the third meters. And if you need a number up there, write a 1. It's 1 kilometer is 1,000 or 10 to the third meters. Any questions? So we've got the equation in. Now you might have an issue of, well, how do I do that on my calculator? 10 to the third. There's all these funny looking buttons. What if I write 1 times in front of 10 to the third? Does that change its quantity? No, because when you multiply by 1, it doesn't change anything. Does this look like scientific notation? We're going to enter that number like it was scientific notation. Now, I haven't gone over this with you. Your calculator. Your calculator should have an EE button or an EXP button. A few of them have a times 10 to the X button. If yours does not have EE or EXP, please come and talk to me, and let's make sure that your times 10 to the X button is doing what it's supposed to. This is not the same as a 10 to the X button. That's something entirely different. But I'm going to talk about EE or EXP. Your calculator will have one or the other. They mean the same thing. Both of them mean times 10 to the. So when you press that button, you say to yourself, times 10 to the. And that'll keep you from throwing extra 10s into all your equations and getting all your answers wrong. So those stand for times 10 to the. So to enter 1 times 10 to the third, let me change colors so it's a little more clear what I'm talking about here. So to put this number in your calculator, you're going to go 1 times 10 to the 3. You do not type in times or 10. You do not use an exponent button. You just use the EE button or the EXP button. 1, and as you push that button, times 10 to the, and then you press the 3. So doing this problem, you're going to put in 5, 6, 7, 8 times 1 if you like, divided by 1 EE3 equals. And that should be 5.678 kilometers. Is your calculator giving you the correct answer? If it's not, you're not communicating it with it. I would encourage you not to do that. You can get the correct answer doing other combinations of buttons. But when the numbers get more complicated, that's going to lead to a lot of mistakes. And the scientific notation works really well. And some of you may say, well, I just took 5, 6, 7, 8 divided by 1,000, and I get the right answer. Yeah, that works too. But we're going to have some numbers that are too large or too small to enter in decimal form, and you will have to use scientific notation. So we might as well just get used to it. Anybody have any questions? Okay, so I'll write it out up here in the red up at the top. So these are the keystrokes. 5, 6, 7, 8, and then the divide button, and 1, the EE button, 3, equals. Now, your calculator might have EXP button instead. Okay? So try it. We have limited time in lecture for me to help you individually with this, but lab is the time where I can help you over and over and over and over again. I have more patience with you guys than I do with my own children. Partly because I see you so much less. Any questions?